For my project, I did the Beckmann rearrangement, which is just dealing with like nitrogen, like amides and stuff like that. So here we have the nitrogen double bonded to a cyclohexane and then an OH group up here. And that electron pair attacks that hydrogen, forcing that, like the hydrogen-oxygen bond of sulfurous acid, as shown here, over back to the oxygen, and that'll come in later. So here, that bond break, like for the positive ion of the OH2, that bond breaks and like goes back into itself, forming a water. And right here, just the ions, or like the lone pair and like double bond shift, creating this triple bonded like nitrogen intermediate right here on the cycle, like hexyl ring, like adding another ring, and so like making it heptane, like a heptic ring kind of sort of thing. And then here the water that was formed from that breaking bond goes to the carbon 1 up here, forming this intermediate, like this water intermediate, like where that's how we get the oxygen for that later. But it forms right here with a water ion because it lost one due to this. So, and then like the ion from previously, like the previous one, like which is now like a nucleophile, it like attacks that hydrogen and like it brings it to itself, creating this like a simple OH with its lone pairs right here. And like basically this reagent keeps forming and reforming itself with like the addition of hydrogen atoms and whatnot. So from here, like with that nitrogen like double bonded and with a lone pair formed from this reagent, from the sulfurous acid, that lone pair attacks that H again, and then the same process as before happens, forming with the sulfurous acid ion, forms like this unstable OH right here, or well, it's just a regular OH, but we want that to be an O. So that lone pair attacks that hydrogen, as well as like that bond forms back there, creating the double bond, and the hydrogen leaves, and then like the double bond from the nitrogen goes into the nitrogen with its lone pair, forming this final product of NH, like right here. And the common reagents and acid used are like tosyl chloride, right here, usually get like ester kind of thing, or like a alcohol more so. Actually no, because the carbon's not there. The thionyl chloride, phosphorus pentachloride, and triethylamine. That was the one used above. Here's some of the intermediates from the last presentation, but in recent literature, the dichloroimidazole iodine dione, which is activated Beckmann rearrangement of ketoxamines for accessing amides and lactanes, is emphasized here. So the group from last time, double bonded N to OH group, mixed with a promoter right here and a methyl cyanide group, as well as under conditions at 80 degrees Celsius from 10 minutes to 5 hours, forming a ketone here with an alkyl group and argon as the R prime, and same over there. So one of the two questions is about catalyzing the reaction. One way to further catalyze the Beckmann rearrangement would be to increase the temperature. With like an increase in temperature, kinetic energy in molecules also increases, and they move faster than previously before, and therefore, by definition, the reaction will move faster. Another method would be like to attain like a stronger acid due to like high toxicity and like leaving group and stuff like that. The reaction would overall react faster and better than if like you would have a weak acid. For IR differences, the major changes would be the double bonded nitrogen to carbon group, as well as like the formation of a ketone later on. So the NC bond, which is sp2 hybridized and have an IR value of like 1640 to 1690, and it'll be a medium to weak bond, and like the OH group of the alcohol will be like 3200 as seen before. The ketone will have like a value around 1720 centimeters minus 1 with a strong peak, and the NHR group will have a value of 3100, which is the product. For the CMR of the starting material, the value would be like 100 ppm because the carbon is double bond attached to a nitrogen as well, and sp2 hybridized. The CNMR final products would be like 170 ppm because of the ketone with an amide group and the R group. For the HNMR starting materials, the value would be like 2 to 4 ppm because of the sp2 hybridized double bond again, and 5 ppm for the OH group. And the final products would exhibit like a value of like 6 ppm because of the new amide group, and the two are right there on the screen. And here are my sources.